lesson in ME Review in Mathematics and Engineering Sciences. Today, I will be discussing about analytic geometry, topic number 4. If you want to know more about algebra, geometry, solid mensuration, and trigonometry, you can watch the previous video discussion. By the end of this lesson, you should be able to recall the fundamental concepts and principles in analytic geometry, list important formula and equations in analytic geometry, and apply concepts, principles, and formula in solving worded problems in analytic geometry. This will be the outline of my presentation. Let's start first with the distance formula. The distance formula is used to get the distance between 2 points in a plane or 2 points in a three-dimensional system. For the distance between 2 points in a plane, say A and B, you can use the coordinates of A and B to get the distance between them. The formula is shown in the screen. On the other hand, for the distance between 2 points in a three-dimensional surface, the formula can also be used, but now we will have to add the third dimension z. Now that we know the distance formula, let's move forward to the slope of a line. The slope is defined as the rise over run. By definition, the slope is equals to the tan of the angle between the rise and the run. And if you're going to use the value of the rise, which is the delta y, that is equals to y2 minus y1. The run, on the other hand, is equals to the horizontal displacement, which is delta x, which is x2 minus x1. So from that, we can get the slope. And if you're also interested in getting the angle between the rise and the run, then you can use the tangent theta. For parallel lines, the slope is the same. For perpendicular lines, meaning the two lines are at 90 degrees with respect to each other, the slope is related in such a way that the other line slope is the negative inverse reciprocal of the other slope. The angle between two lines. For the angle between two lines, say for example, the line I1 and I2 here in the presentation with each corresponding equations. From those two equations, we can get also the slope of the line. So, the angle between two lines using the slope of the two lines can be written in such a way that tan theta is equals to the slope of the second line minus the slope of the first line divided by 1 plus the product of the two slopes. The distance between a point and a line. For the distance between a point and a line, we are referring to the perpendicular distance, the nearest distance between the given point. Say for example, the point here in the illustration with the coordinate x1, y1, and the distance t to the known line with the given equation ax plus by plus c. So if we have this case, then we can use the formula distance is equals to ax sub 1 plus by sub 1 plus c divided by positive negative the square root of a squared plus b squared. So the value of a, b, and c is the coefficient of the given line, which is a, b, and c. Take note that we have to include the sign. So if it is a negative value, then we will have to use the negative value here in the equation. For the value of x sub 1, we will use the value of x sub 1 from the given point. For the y sub 1, it is the value of y in the given point also. So in using this formula, we should take note that if we can use positive for the positive negative sign here if B is positive and the point is above the line or to the right of the line, just like this one. We will use positive also if B is negative and the point is below the line or to the left of the line. Otherwise, we will use a negative value. So meaning, if it will not satisfy the two cases here, then we will use the negative here for the denominator. So that is how we can get the distance between a point and a line. The distance between two parallel lines. Say for example, you have here two parallel lines. So the distance between them is also the perpendicular distance, but as you can observe, it is just equals all throughout since they are parallel. Say that the first line has equation y is equals to mx plus c1, and the second line is y is equal to mx plus c2. We can observe that they have the same slope because, as you can still recall, parallel lines have the same slope. That's why they have the same slope here. However, they can have different value for the y-intercept. So that's the difference between the two. And say for example, you have two parallel lines with the equations ax plus by plus c1 and ax plus by plus c2. Then the distance between these two parallel lines is equals to c1 minus c2 over the positive negative square root of a squared plus b squared. So the c1 is the value of the coefficient of c for the first equation, and c2 is the coefficient c2 in the second equation. A and b is the same for both lines since they are parallel. We use the sign either positive or negative that would make the distance positive. For the line segments, the coordinates of point that divide a line segment, say for example this line segment here between x sub 1, y sub 1 and x sub 2, y sub 2. Say for example that we divide this line with this point denoted by this point here xy, and in such a way that they are now divided into two segments with distances r1 and r2. Then the value of x here in the point dividing this line segment is equivalent to this equation here. We will just substitute the length of this r1 and r2 and also the value of x sub 1 and x sub 2. For y, we will also use the an analogous formula, but this time we'll use the value of y sub 1 and y sub 2. So that is how we can get the coordinate of a point that divide a line segment. A special case of this is what we call the midpoint between the line segment. If the line is divided in such a way that the point is at the halfway, the 2 points, then that is the midpoint. Then we can use the midpoint formula, which is just simply written as the half of the sum of x sub 1 and x sub 2 for x, and for y is the sum y sub 1, y sub 2 divided by 2. Let's move forward to the areas of a polygon using the vertices. Say for example, you have a polygon which can either be a triangle, a square, a pentagon, hexagon, in such a way that the vertices are given, just like what you can see here. Then you can use the formula that's flashed in the screen to get the area of that particular polygon. So we will simply use this formula. So the arrow shown here in the figure moving in a counterclockwise direction indicates that the vertices must also be written in the equation below in a counterclockwise direction. So that's why when we write it here, it is also in a counterclockwise direction. So if it is a square, then you have to add here x sub 4 over y sub 4 and then the x sub 1, y sub 1. Then to get the equation here, what we're going to do is just we will add all of this value that's shown here in this arrow that's moving downward, all of that. So you can see those are all the value here. So the x sub 1, y sub 2 is this portion here, and then we have the x sub 2, y sub 3, and then we have here the x sub 3 y sub 1, then minus the other part, so this one, so y sub 1 x sub 2, and then we have the y sub 2 x sub 3, and finally we have the y sub 3 x sub 1. So again, you can add more if we have more sides for the polygon. So you will just substitute the value of those coordinates here and divided it by 2. Then that's how you can get the area of the polygon using the coordinates of its vertices. Let's move forward to the different equations of a line. So the general equation of a line is ax plus by is equals to c. For the point slope form of the equation of a line, this is the form of the equation wherein we're given with a slope m and a point, which is denoted by x sub 1, y sub 1. So if we have a point and a slope of a given line, then we can get the equation using the point slope form. If we are given with us intercept and the slope, then we will use the slope intercept form. So here we're given with the slope and the y-intercept b. And then finally, if we're given with the intercepts, x-intercept and y-intercept, then we will use this format. So take note that the intercepts are the point wherein the line passes through the x-axis or to the y-axis. So that's the intercept of a line. So whatever the given is, if you're going to look for the equation of a line, then you can use any of this equation. You will then just simply simplify such that you will obtain the general equation of the line. Now that we are already familiar with lines, we can now move forward to the conic section. Take note that all of the remaining topics, circle, parabola, ellipse, and hyperbola, belong to the conic section. As you can see here in this figure, the conic section is actually formed from these conics here. That's why they are called conic section. So we have here a circle formed by cutting a surface that is parallel to the conic, and we have an ellipse if we cut it diagonally in such a way that it will not touch the bases. And then we have the parabola and also the hyperbola if we cut it on these directions that you can show here in the see here in the presentation. So the general equation of the conics is given by this equation here. For this equation, if we are going to get the value of b squared minus 4ac, which is the determinant, the b, which is the value of the coefficient of xy here in the general equation, a is the coefficient of x squared, and c is the coefficient of y squared. Therefore, we can get the conic section based on the given value from the general equation. If the b squared minus 4ac is less than 0, that would mean that the eccentricity would be less than 1. Then the conic section would be ellipse. On the other hand, if b squared minus 4ac is greater than 0, the eccentricity would be greater than 1. Then the conic section is an ellipse. And finally, if b squared minus 4ac is equals to 0, then the eccentricity would be equals to 1. Then our conic section would be equal to a parabola. Take note that in the general equation, when b is not equal to 0, then the principal axes of the conic are inclined, meaning it is not parallel to the coordinate axis. When b is equal to 0, then the principal axes of the conic are parallel to coordinates axes x and y. If a is equals to c, meaning the coefficient of x squared and y squared is equal, then the conic is a circle. If a is not equal to c, but they have the same sign, then the conic is an ellipse. If a and c have different signs, and the conic would be a hyperbola. So that's how you can get the kind of conic section being described by the conic section by inspecting the value of the coefficient of x squared and y squared in our general equation. On the other hand, if either a or c is 0, the conic is a parabola. So meaning one of the x squared and y squared is 0, meaning it does not exist, then the conic would become a parabola. So if a is equal to c, we have a circle. If a is not equal to c, same sign, they will be ellipse. If a and c have different signs, then the conic is a hyperbola. If either a or c is 0, then the conic is a parabola. Let's dig deeper to a conic section called circle. So this is how the circle looks like. The conic of a circle on an xy coordinate axis. The center of the circle is denoted by HK, and our radius is denoted by R. So the general equation for the circle is shown also here. So you can see that the value of the coefficient of x squared and y squared is equal, and they also have the same sign. So they are positive a here in this general equation, then the equation is a circle. The standard equation, on the other hand, for a circle is x minus h squared plus y minus k squared is equals to r squared. This is when the center of the circle hk is known and the radius is also known. Then you can get the standard equation by plugging in the value, and you can get also the value by completing the square from the general equation. The alternate formula in finding the center and the radius of a circle is shown here. For the center hk, we can use the value of the coefficients of d, a, e, and a. So we will base it in the general equation of the circle. For the r squared or the radius, we can also use the vertex, which is we can find the value from this alternate formula, and also the value of f and a in the general equation of a circle. Let's move forward to parabola. This is the general equation of the parabola with the axis of symmetry that is vertical and axis of symmetry that is horizontal. So when the axis of symmetry is vertical, that you can see here, for example, whether it is opening upward or downward, then the equation would be like this. So you can see that the y is equals to 0 and that the x squared term is present. On the other hand, if the axis of symmetry is horizontal, just like this axis of symmetry here, then the parabola would face to the left or to the right. Then the value of x squared in the general equation would be 0 in such a way that y squared will be present. And this is how the equation would look like. So the remaining part of the general equation is just the same. So it is just the first term that is different. So we have the vertical axis and we also have a horizontal axis parabola. If we have the general equation, we also have the standard equation. For the standard equation, when the axis is vertical, this is how we can write the standard equation. So now the x squared is present, the y squared is not present. The axis is horizontal, you can see that the y squared here is present, the x squared is not present. So take note that the value here, positive, negative, is an indication whether it's opening up or down. So if it is positive, if the axis is vertical, then it would open up. If it is negative, then it would open down. On the other hand, if the axis is horizontal, just like this, if it is positive, then it would open to the right. If it is negative, it would open to the left. The alternate formula for finding the vertex of the parabola is shown here. So you can use the d, a, e, and c coefficient of the general equation of the parabola. Same also with the k. So we also have this what we call eccentricity. So a circle, for example, has an eccentricity of 0. So the eccentricity shows you how uncircular the curve is. So for the eccentricity of a parabola, it is always equals to 1. For the latus rectum is shown here. It is the line that passes through the focus. So this is the focus and is perpendicular to the axis of the parabola. And this one is the axis of the parabola. So the two of these actually is a hyperbola, but if you look at this part only, this would be a parabola. So we have here the latus rectum perpendicular to the axis and passing through the focal focus. So that is the latus rectum. So the latus rectum is 4 times the value of P. So that's how we can get the value of the latus rectum. So P can also be derived from the general equation or the standard equation of the equation of the parabola. So here, this A here is actually the P. So because our P is just the distance from the vertex to the focus. So that's the value of our P. So to understand better what eccentricity of conic section means, so this is how it means. So for a circle, the eccentricity would be equal to 0 because it's perfectly circle. For ellipse, on the other hand, the eccentricity would deviate from 0 to, say for example, 0.5. Then we have here a parabola, which has an eccentricity of 1. Hyperbola, we have a eccentricity of 2. And a perpendicular vertical line has an eccentricity of infinity. So basically, eccentricity is just really the how uncircular the curve is. Now let's move forward to ellipse. So this is how the ellipse look like. So the general equation for the ellipse is shown here. You can see that the term x squared and y squared is present, just like a circle. However, a is not equal to c. So they also have to have the same sign. So a and c is not equal and they have the same sign, then that is an ellipse. For the center, we can get the value of h and k using the value of d here, and a and also e and c from the general equation. Simply substitute those values here, then we can get the center of this particular ellipse. The major axis, the standard equation, if the major axis is horizontal, is shown here. So this is how the ellipse would look like if the major axis is horizontal. So the major axis is this axis here. So that is the major axis. And then the other axis is the minor axis. So the major axis is called major axis because it's longer always than the minor axis, whether it is vertical or horizontal ellipse. So that would always be the case. If it is just half, then it's the semi-major axis or the semi-minor axis. So here, for example, the A and B are semi-major axis and semi-minor axis. So they are semi, meaning they are half of the major and the minor axis. So for if the major axis is horizontal, you can see that the term below the x minus h squared is the semi-major axis squared. So it's a squared, or the longer axis, the half of the major axis, which is a squared. On the other hand, if the major axis is vertical, just like here, the equation would be like this. So our x minus h squared will be divided by the minor axis squared, or the b squared. The sign is always positive in between them, and the value on the right side would always be 1. So take note that A is always greater than B for the ellipse. And you can get the relationship between A and B and C by using the relationship A squared is equals to B squared plus C squared, where C is the distance from the foci to the center. So the focus here to the center of the ellipse, that is our value C. So you can get that value by using the relationship here. If you have the semi-major axis and the semi-minor axis. The length of the semi-major axis and the semi-minor axis can also be derived using the general equation. So you can use whichever is lower between the square root of A and C. So take note that A is always greater than B. So if you're going to take the square root of A and the square root of C, whatever is higher, that would be the semi-major axis, and whatever is lower, that would automatically be the semi-minor axis. The area, on the other hand, for the ellipse is simply pi AB. Then we also have the eccentricity of the ellipse. The eccentricity is defined as C over A. That would always be less than 1. So take note that the relationship of A, B, and C is given in the previous slide. For the latus rectum, so this is the latus rectum. So it is still the line that passes through the major axis perpendicular to that and passing through the focal point. So that's the latus rectum, and it can be derived using the formula 2b squared over A. Again, A is always greater than B. Now let's move forward to hyperbola. So this is how a hyperbola looks like, as well as the different parts. We can see here if it is a parabola, hyperbola with transverse axis that is horizontal. So this is the illustration for a hyperbola with transverse axis horizontal, because this part here is the transverse axis. So if it is perpendicular, if it is vertical, then it would be transverse axis vertical hyperbola. So the different parts are the directrix, the asymptote. We also have here the conjugate axis. So for the general equation for a hyperbola with transverse axis horizontal, just like this one, is shown here. So you can see that A and C is not equal, and they have opposite sign. So that is hyperbola. So if it is positive, then that would become an ellipse. The transverse axis vertical equation is also shown here. So you can readily spot whether it's ellipse or hyperbola based on the equation. For the standard equation for transverse axis horizontal hyperbola, it would be written this way. If it is a transverse axis vertical, then it would be written this way. So you can see here that unlike the ellipse, the sign in between them would be negative. So the value of A here is this portion that you can see here. It's the A here in this formula. The B is the conjugate, this axis here that you can see. That's the conjugate axis, and we also have the transverse axis. So the transverse axis is passing through the transverse axis. Then we also have this, the B is passing through the conjugate axis. So that's how you can get A and B. So the length of the transverse axis, if it is a horizontal hyperbola, if it is vertical, also for the length of the conjugate axis is shown here in the presentation. The eccentricity is still C over A, and that's always greater than 1. So the C is the distance from the foci to the center, or the focus. So this is the focus, and its distance to the center is equals to C. Then you can find now that C is greater than either A or B, such that the relationship between them would be C squared is equals to A squared plus B squared. So it is now different relationship as compared to the relationship in the ellipse, wherein your C is smaller than A. So this is how you can get the value of C if you have the value of A and B. So again, A is this line here and B is this line here. If you can see, the A is just the distance from the vertex to the center, and B is the distance from the co-vertex to the center. The distance from the center to the focus is equals to C. So let us have some example for us to better understand how to use those formula of lines and the conic section. Let's have an example. If the distance between 2 points 3y and 8, 7 is 13, then y is equals to, so from the distance formula, we can see that this is the distance between 2 points on a plane. So we will use the formula that you can see here flash in the screen. So we substitute the value of x sub 1, x sub 2, y sub 1, and y sub 2. So upon substituting the value, you can find that from our distance formula, the only unknown value is the y1. So we will solve for the value of y sub 1 by using any algebraic manipulation technique. Then the value of y sub 1 would be equals to 19 or -5. So it means that the distance between 8, 7 to the point 3, 19 or 3, -5 is equals to positive 13. Then we have sample problem number 2. So find the inclination of the line passing through -5, 3, and 10, 7. So from the definition of the slope of a line, the slope is simply the tangent of the theta, which is also equals to y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Substituting those values and solving for the value of theta, we can get the inclination of the line that passes between the 2 points, and that is equals to 14.93 degrees. Sample problem number 3. What is the length of the line with a slope 4/3 from a point 64 to the y-axis? So you can see here the illustration of this problem. So we have this point 64 and the point 0, -y, which is a point on the y-axis. So we are looking for the distance between this 0, -y to 64 if the slope of this line is m, which is 4/3. So from the equation of the line using the point slope form, since we are given with the slope and the point, then basically we can get the equation of this line, and that is 1 y minus y sub 1 is equals to m multiplied to x minus x sub 1, substituting the value from the given and also simplifying that so that we can get the general equation written in the slope intercept form, since we have here the slope 4/3 and the intercept -4. So we wrote this in this form because we are interested in getting the value of the intercept y. So from this equation, we can find that the y-intercept is 0, -4. So the value of -y here is -4. So using the distance formula, we can now get the distance between 0, -4 and 6, 4. So we will just simply plug in the value to the distance formula between these 2 points and solving for the distance. So the distance is 10 units. Sample problem number 4. Find the equation of the line if the x-intercept and the y-intercept are -2 and 4 respectively. So to illustrate what x-intercept and y-intercept are, you can see here that where they are located. So for the x-intercept, it is the point that passes through the x-axis. The y-intercept is the point on the line that passes through the y-intercept. So for the general equation using the intercept form of the line, it is defined as x over a plus y over b is equals to 1. Since the x-intercept a and the y-intercept b are given, then we will just substitute them in that general equation, in that formula, and simplify them in such a way that we can find the general equation. So the general equation is y minus 2x minus 4 is equals to c. Sample problem number 5. What is the radius of a circle with the following equation? So this is a circle because if you're going to look at it, the term x squared and y squared have the same coefficient, which is 1, and they are both positive. So this is a circle. So for the radius of a circle, we can use completing of the square in such a way that we can condense this general equation into the standard equation. So by completing the square, we will reduce the general equation in this form. So what we did is simply we divide we separate those term that has x or x squared, and also those term that has y or y squared, and we put all the constant value on the right side. So just like here, so for x squared minus 6x, to complete the square, we'll simply divide 6 by 2 and take the square of that. So 6 divided by 2, that is 3. So that's why we have here 3. And then we have a minus sign because the sign between them is negative. And we will put the square of 3 squared here on the right side because we added the positive 3 also here, so we will add positive 3 also here. Same also with those that that involves y squared or y. So simply divide 4 by 2, that's why we have 2 here, and square it and put that value here. So we were able to complete the square. We will simplify this equation such that we will obtain this one. And then we are going to reduce it into the standard form, wherein we're going to get the square root of 25 so that we can get the radius. So by observing this standard equation, so now this is the standard equation. We have the h here is equals to 3. So that is our vertex, center of the circle, and we have our k is equals to 2. So the center of the circle is at 3, 2, and the radius is equals to 5. So if we're going to get the value of the radius by inspecting the equation, r is equals to 5 because this is the standard equation of the circle. So r would be equals to 5 because this is the r here on the right side, and this is equals to the r. So that is how you can use completing the square in order to get the radius of the circle. But you can also use an alternative solution by using the general equation for a circle. So this is the general equation of a circle, and you can see that it is analogous to what we are given here. Simply we are going to use the formula h is equals to the negative of this term that has the value of x. So the negative the negative is a general formula. Since we have negative here, that's why we have a negative value here, divided by 2a. A is the coefficient of x squared, so that's why we have h is equals to positive 3. On the other hand, for k, that is simply the coefficient of y, which is negative 4, divided by 2a. So a is still the a here. No, this one here, because they are just the same anyway. So we can get the value of k. So from the value of h and k, then we will use the formula h squared plus k squared minus the negative minus this term here, which is the f over the value of our a or c. So from that we can get also the radius is equals to 5. So whatever is more comfortable with you, you can use that equation to get the center, h and k, as well as the radius from the general or the standard equation of a circle. Sample problem number 6. An Earth satellite has an apogee of 40,000 km and a perigee of 6,600 km. assuming that the radius of the Earth is 6,400 kilometer, what will be the eccentricity of the elliptical path described by the satellite with the center of the Earth at one of the foci? So this is how it is illustrated. We have the center of the Earth at one of the foci. This is the focus 1, and then we have another focus. This point here is the center. So the Earth is at the foci. So the perigee is this distance here, which is the lowest distance between the surface of the Earth and that of the satellite. So that is the perigee. The apogee, on the other hand, is the longest distance from the Earth to the satellite. So from the given, the perigee is 6,600. The apogee is 40,000. So the radius of the Earth is 6,400. That's why this distance here is the diameter of the Earth is just times 2 of that value, which is 12,800. And we are looking for the eccentricity of the elliptical path described by the satellite. So for the major axis of the ellipse is that is equals to 2a. So this 2a here, because if you can see, this is equivalent to the major axis. This is simply the sum of this 40,000 kilometer, this 12,800 kilometer, and this 6,600 kilometer. So that's the value of the semi-major axis. So we divide it by 2, so we can get the semi-major axis. For the focal distance is the distance from the focus to the center, and that is equals to c. So this is c here, or the distance from the center of the Earth to the center of this elliptical path. So that is the focal distance. So if you can observe, the focal distance is equals to the value of a, this a here, or you can use this a, minus the 6,600 plus 6,400. Because if you're going to look at it, if this is a, if the distance from this one to here is a, then our c would be equals to a minus this 6,600 here, and this the radius of the Earth, that is 6,400. So this is how we can get the value of c. So that is the c. So the focal distance is equal to 6,700 kilometer. So from the definition, the eccentricity of the ellipse is simply c over a, or the focal distance divided by the semi-major axis. So the eccentricity of the elliptical path is 0.56, and it makes sense because the eccentricity of an ellipse is less than 1, but not greater than but is not less than 0. So that's why it's between 0 and 1. So it's 0.56 here in this case. Find the general equation of a circle with center 1, 2, and radius 5. So the standard equation for a circle is shown here. So we will simply substitute the value of the center, hk, and also the radius. Take note that the minus sign here is part of the general equation, meaning if it is a positive, we'll simply substitute those values and also the radius. And we're going to get already the, if you're going to expand this whole equation, standard equation, then you can get the general equation. So the general equation is x squared plus y squared minus 2x minus 4y minus 20 is equal to 0. So by inspection, you can see here that x and y has the same sign and they are equal coefficients, so therefore this is a circle. Sample problem number 8. Find the center of the ellipse. 9x squared plus 25y squared plus 18x minus 100y is equal to 116. If you can see, this is an ellipse because the coefficient of x squared and y squared is not equal and they have the same sign. If they have opposite sign, this would be a hyperbola. So to get the center from the general equation for the ellipse, we will use the shortcut formula. So which is the h is negative d over 2a. So we'll simply get the d is the coefficient of x. So from our equation, that is equals to 18. A is the coefficient of x squared, and that is equals to 9 here. So that's why we have 9 here. So we get the the value of x for the value of k of the center of the ellipse, that is negative e over 2c. So e is the coefficient of y, so we can see here that the coefficient of y is negative 100, so that's why we have here negative 100. C is the coefficient of y squared here in the general equation for the ellipse, and that is equals to 25, so we substitute it here, then we can get the value of k. So from that, we were able to get the center of the ellipse as negative 1, 2. You can also use completing the square and verify whether the formula is correct. Reduce the equation of a parabola y squared minus 4y minus 12x minus 32 is equals to 0 to the standard form. So using completing the square, we are going to complete the y and the x term of the given parabola. So you can see here, since we have minus 4y, we divide it by 2 and we square it. And we also add that value on the right side, because if we add something here on the left, then we will also add that one on the right. The two values here, we put it on the right side so that the left term will be composed of the y coefficients, quite a variable. Then we simplify so that we can obtain y squared minus 4y plus 4 is equals to 12x plus 36. We can simplify it further. We can move the value of 4 on the right side, then we can extract the value of 12 so that we can get y minus 2 squared is equals to 12x plus 3. So take note that this term here is actually equals to y minus 2 squared. And on the right side we extract the 12, that's why we have 12 here, so that the remaining in the equation would be x, and 36 divided by 12 would be 3. So this is now a standard form of the equation of the parabola. So you can also see that since the x squared is 0, then this parabola would face, and it's positive here, it would face to the right. What conic section is represented by 4x squared minus y squared plus 8x plus 4y is equals to 15. So by inspection, since a is not equals to b and they have opposite sign, then the equation is a hyperbola. So as a summary, this lesson we were actually able to discuss lines and the conic sections.